My name is Bobby Woolf. I work for IBM, and today I'm going to talk about Kubernetes operators. What are they good for? First of all, what is an operator? As far as Kubernetes is concerned, an operator is just an application. But what we know is that it's an application that we have written to manage other applications. We've written it to customize it for the application that it manages. That application that the operator manages is called the operand. And it's typically a backing service. It's a stateful workload that your stateless application uses. Part of what's cool about operators is that an operator works the way Kubernetes does. An operator effectively extends Kubernetes to teach it how to manage this particular operand, this particular stateful service. So what makes operators helpful? What's really cool about an operator is that it makes a service self-managing. The operator embeds domain-specific knowledge about how the service works and about how to manage the service's lifecycle. It knows how to install the service, upgrade it, keep it running, track its metrics, and so on. So in this way, the service knows how to manage itself because the operator is managing the service. This is really important in hybrid cloud. In public cloud, it may not seem so important because when you create a service in a public cloud, the cloud vendor manages the service for you. They know how to install it, keep it running, all that kind of stuff. But in hybrid cloud, when you install a service, you're actually installing it into your environment. And from there on, you, the customer, are responsible for managing the service, installing it, keeping it running, upgrading to new releases, all that kind of stuff. And this is something that as a customer using the service, you may not want to do. You may not have the staff with the bandwidth to do it. Your staff may not have the skills to do it. They may not be interested in doing it. They know how, they just don't want to. They've got other things they want to concentrate on. They don't feel like having to manage all the services that the application is using. So for these sorts of customers, a service that can manage itself is much more appealing. So who can benefit from operators? Anybody who's developing a service that they're going to deploy in any kind of service catalog, they can benefit by developing an operator for their service to make it more self-managing. Because the more self-managing your service is, the easier it's going to be for your customers to use it. Two examples of service catalogs. One is operatorhub.io. It's basically the Docker hub of operators. And another example is the Red Hat Marketplace, which is basically the app store for Red Hat OpenShift. So if you're developing services and you want to put them in a service catalog like this, and you want them to be self-managing so that customers have an easier time using them, then operators are going to help you do that. To understand the benefit that we're getting from operators, let's first take a step back and talk about the benefit that Kubernetes gives you. The way you deploy an application to Kubernetes is that you describe the application to Kubernetes and you say, gee, it would be nice if it were running. Kubernetes has a very declarative model. So you don't tell Kubernetes what to do, you describe to Kubernetes what you would like to have done, and then Kubernetes figures out how to do it. So for example, if you have a microservice and you want to run it in 3 replicas, you tell Kubernetes that's what you want. It's Kubernetes, the cluster, that looks at how many replicas are running, realizes there are none running, and so it starts up 3 of them. You don't actually tell it to start 3. You just tell it that you want to have 3 running. It looks at how many are running and decides what changes to make, and so that there are now 3 replicas running. One way you can see this happen is that if you got 3 replicas running and you go and delete a replica manually, Kubernetes sees this as a problem and it starts up a replacement. Because Kubernetes had 3 replicas running the way you wanted, then one of them stopped running because you deleted it. And so then Kubernetes started up a replacement to put it back to 3 again. And this is a really neat feature of the way Kubernetes works because it enables Kubernetes to manage your application and keep it running even under adverse circumstances. So while your application is running, if a pod crashes, Kubernetes detects that and starts up a replacement. It does that automatically. You don't have to do anything, it just figures that out. Likewise, if an entire node crashes, the cluster figures out all the pods that were running on that node and restarts them on other nodes. Again, it does all that automatically. And mostly what we're talking about is the way Kubernetes keeps pods running, but also there's other Kubernetes objects that the pod uses, services, config maps, secrets, those sorts of things. Well, Kubernetes makes sure to keep those available as well. So Kubernetes is managing your whole app for you. All you have to do is describe to Kubernetes the structure of your app and how to deploy it, and then tell it that you want it to run. And then Kubernetes makes sure to run that application for you, even as things are going wrong. It'll keep the application running as best it can. Now, how does Kubernetes do all this? It, it does it using controllers. So the way controllers work are Kubernetes actually maintains two kinds of state, desired state and current state. So desired state is what you as an administrator get to specify. Here's what I want to have running. Current state is what Kubernetes manages. Here's what actually is running. So in desired state, you say, I want to have 3 replicas. Current state is Kubernetes confirms, all right, I have 3 replicas running. The way it does that is through a process called reconciliation. That when current state is different from desired state, then Kubernetes changes the current state to make it match the desired state. The code for doing all this is in the part of Kubernetes called, in the part of the cluster that's called the control plane. The control plane manages the worker nodes. It is the brains of the cluster. Some of the main things that are running in the control plane are controllers. A controller knows how to reconcile desired state into current state. There's a bunch of different controllers. They're responsible for managing different parts of the cluster, different kinds of objects, but all of them do the same thing as far as all of them make sure that the current state matches the desired state, and reconciliation makes changes to the current state to make it match the desired state. Now, all of these controllers are run by a thing called the controller manager, which is also in the control plane. The controller manager knows the list of controllers, and it iterates over them constantly in an infinite loop called the control loop, where for each controller, it tells it to reconcile itself. So for this reason, we call the whole thing the reconciliation loop. And reconcile is where the controller, each controller does reconciliation. So when the controller manager tells a controller to reconcile itself, then the controller looks at the current state that it's responsible for, compares it to the desired state, and if there's any differences, then it issues commands to change the current state to try to make it match the desired state. And this is constantly running over and over in an infinite loop inside of the inside of the control plane, run by the controller manager. Another thing that Kubernetes does really well is that it's able to perform rolling updates for you automatically. So the way you do that is when you deploy your application, you actually do it as a deployment. And when that deployment gets created, it creates a replica set for managing the pods that are running the image that you've deployed. So that's replica set 1. So you come up with a new version of your image, you want to deploy that, you deploy it in the same deployment, and what the deployment does is it creates replica set 2, which is going to run pods using the new image instead of the old one. What Kubernetes does not do is shut down all the old pods and start up a bunch of new pods, because if it did that, then the user would experience an outage. Clients would not get requests fulfilled while all the pods are down. So instead, what Kubernetes does is it starts up a couple of new pods in replica set 2, and then it shuts down a couple of pods in replica set 1. And it does that over and over and over, usually in 3 or 4 phases of starting up new pods and shutting down old pods. And in that process, what it's doing is it's converting all the client requests. It's moving them from the old pods to the new ones, from the old image to the new one. By doing it this way, there's always a bunch of pods running, and so the clients always get their requests fulfilled. They don't experience an outage. They experience zero downtime. And that's a really nice feature of Kubernetes. Now, Why am I talking about these features of Kubernetes, and what does this have to do with operators? Well, I'm glad you asked. The thing is that when we were talking about how Kubernetes manages an application, a assumption there is that the application is a stateless workload. It has no state. The problem with these services, these backing services that we want to be able to deploy, is that they are stateful workloads. And stateful workloads, stateful apps, those are a problem. Kubernetes is designed to manage stateless workloads, and it's really good at it. And that's what these controllers in the control plane are doing, is they're managing the pod replicas. And because they're stateless, they're all the same. They're all running the same code. They don't have any state, so they're all the same. The control plane is real good at doing that. The problem is stateful applications. The control plane doesn't know how to manage those. And the problem with stateful applications is that not all the pod replicas are the same. They can be different. There's two ways that happens. Let's use MongoDB as an example. MongoDB runs as a cluster of pods, like most anything else in Kubernetes, but the pods are not all the same. There's one container that is the primary, exactly one, and then there are 0 more other pod replicas that are the secondaries. The primary has to start first, and then when the secondaries start, they all have to federate into the primary. So that gets to be some pretty complicated logic to manage all that. It gets even worse when something goes wrong. That if the primary goes down, then if a secondary goes down, you can pretty much just replace it. But if the primary goes down, then the secondaries have to get together and elect a primary and convert one of them to the primary, and exactly one. And then all the other secondaries have to federate to that new primary. So it's kind of a pain. Another thing that's going on is that each of these pods, whether it's a primary or secondary, has state, and that state needs to be persisted somewhere. So in Kubernetes, that's persisted in a state. The state is stored in what's called a PV, a persistent volume. So that's a piece of disk that stores the data. And each pod connects to a PV via PVC, a persistent volume claim, to help make sure that only one pod connects to any one PV. So even if two pods have the same data, they still have two different PVs that have two separate copies of the data. And so there's a real problem here whenever you're replacing pods of making sure that each one connects to existing PVs and that they don't become orphaned and that you don't have two pods connected to the same PV and this sort of mess. So managing a stateful application is much more complicated than managing a stateless application. And managing a stateful application is custom for every stateful application. What I've described now, is the way MongoDB works, more or less. Any other stateful application works differently. And so it's very hard for Kubernetes to know how to manage that. In fact, basically Kubernetes can't. That, long story short, you need people to do it. So you have somebody called a site reliability engineer, an SRE, and that person's job, among other things, is to manage the stateful apps. They do it using manual steps, and it's very custom for each workload. And it's a fair amount of work. And that's kind of unfortunate. So stateful apps are a pain. Kubernetes is good at managing stateless apps. Stateful apps, it's a lot harder. Good news, operators are for managing stateful apps. So again, an operator is custom code that you've written specifically to manage a particular stateful app. Each stateful app is going to have its own operator, and each operator is going to be implemented differently because it knows how to manage that particular stateful app. By implementing an operator for a service, the operator makes that service more self-managing. It does a lot of the management for the service so that the customer that's using the service doesn't have to manage it. Their SRE doesn't have to manage it. The operator manages the service. Again, the service is what we call the operand. That is the service that is being managed by the operator. So for example, with MongoDB, we can have multiple MongoDB database instances, multiple databases. Those are all operands. They can all be managed by a single MongoDB operator, at least assuming they're all in the same cluster. Now, when you have multiple instances, they're actually different from each other somewhat. They have different names and different network addresses and things like that. And so, they can't be exactly the same. Well, so those are variables. Those are things about the configuration of a particular instance that is different from the other instances. Operators, ultimately, what they do is they automate an SRE's toil. And so here's the definition of toil, comes from Google. And let me highlight a word in there, automatable. So an SRE has to do a lot of routine work, which is fairly manual, it's fairly routine, it's fairly boring, it's the same thing over and over again. That's what they call toil. The idea is to try to automate toil so that the SRE doesn't have to perform it manually, but rather so that the system performs it automatically for the SRE, so the SRE can go home at night and sleep and not have to be doing this 24/7. So what an operator does is it automates the toil that otherwise would have to be performed by the SRE. If it's a really good operator, it'll automate most of the toil. If it's a so-so operator, it automates some of the toil, but some is better than none. The better you make your operator, the more toil that it'll be able to automate, the less toil that the SRE will have to do. One thing to keep in mind about operators is that they're not magical. In order for an operator to be able to manage a service, there has to be a way to manage the service manually. Ultimately, what an operator does is it automates what an SRE can do manually. But if you have a service that just something can't be done, well, then an operator is not going to be able to do it either. So the service, first of all, has to be fairly sophisticated so that it can be managed. Second of all, an SRE needs to be able to manage it manually. And third of all, an operator can automate a lot of that management so that the SRE doesn't have to do it manually. So here's the structure of what an operator looks like. Again, keep in mind that as far as Kubernetes is concerned, an operator is just an application. It's a image and a bunch of Kubernetes objects that are expressed as YAML, and you deploy them all into the cluster, and the cluster runs them. Now, the main programming artifact inside of an operator is called the controller. It's the heart of the operator. And the main method inside the controller is called reconcile, and it's the heart of the controller. So reconcile is the heart of the controller, which is the heart of the operator. Now, besides the controller, there's also a custom resource definition. And what it does is it defines the schema for the controller's API. These are the variables that the operator needs. These are the variables that make one instance of the operand different from another instance of the operand. The CRD defines what those variables are. Then to use an operator, you specify a CR, a custom resource. And a CR specifies the value for those variables. So as we can see here in this example, one of the variables is size, which is an integer. And then the CR specifies that the size in this case is 3. In another case, it might be 5. In another case, it might be 20. Those are different CRs that all fit the same CRD. One thing to keep in mind here is that CRs and CRD are a Kubernetes feature that existed before operators. So operators are taking this feature and leveraging it to make operators work better. But again, this is part of how Kubernetes work. This is part of how operators work the way Kubernetes does. Effectively, they extend Kubernetes. Is they're making use of this feature that it already has, CRDs that can have CRs. Now, the variables that are in the CR, well, let me put it this way. The CRD itself is the API for the controller, and that is expressed programmatically in the controller as a separate API object, which is just a big dumb data object that stores variables. And the values for those variables come from the CR. So effectively what the operator is going to do is it's going to read the values out of the CR and store them in the API so the controller can use them. Another part of this is there's a couple of RBAC artifacts. Mostly it comes down to service account. So again, RBAC and roles and service counts are all things that are built into Kubernetes that existed before operators came along. Operators are just leveraging those. And basically what the operator is doing is it's using the service count to be able to talk to the Kube API to tell it to create resources. So if you know how a service count works, it's the same thing here. If you don't know how a service count works, go brush up on that. And when you understand what you can do with a service count and with the Kube API, then you'll understand what the controller is doing to use the Kube API via a service account. Let's go back to the idea that operators extend Kubernetes, that operators work the way Kubernetes does, and it extends them. The way it's doing that is that each operator defines a custom resource and a custom controller. So the custom resource is defined ultimately as a CRD, that's the schema. And then when you create a CRD, what you're doing is you're creating a new kind within Kubernetes. So a new kind of object. You're not creating the object, you're creating the kind that says, here's what instances of this object would look like. So the way that's specified in Kubernetes is as group version kind. You're real familiar with this if you've written the YAML for deploying stuff into Kubernetes. For example, a deployment is in the namespace apps and v1. When you write your own CRD, you need to come up with your own namespace and version. So here we're saying cacheexample.com, and we're saying the version is v1 alpha 1. Cacheexample.com, that would be whatever company you work for. That would be their domain. And then the version is whatever version you want to use to keep versions separated from each other. And then memcache D in this example is the name of the kind. So this is the CRD for describing memcache D instances. Before we were talking about MongoDB, there would be a CRD for describing MongoDB instances. So each operator has a controller. And when you deploy the operator, what it does is it adds its controller to the controller manager that's in the control plane. The controller manager has a list of the controllers in the control plane. Well, now it adds the custom controller from the operator to its list of controllers. And what that means is that as the controller manager runs the control loop to do reconciliation, not only is it telling the controllers in the control plane to reconcile themselves, but then it's also telling the custom controllers and the operators to reconcile themselves. So now the operators are part of the control loop. So that infinite loop that Kubernetes uses to keep its current state aligned with its desired state, well, now the operators are part of that. And whereas the controllers in the control plane manage certain features that are built into Kubernetes, now the controllers from the custom controllers from the operators are able to manage the things that they manage, which is our stateful workloads, our services. There's 5 levels of maturity or capabilities for operators. So you see them here on the screen, 1 through 5. Basic idea is that the simplest operator knows how to install its service. Level 2 is it knows how to upgrade its service. Level 3 is that because the service has state, it can do things like back up that state automatically on some schedule. Level 4 is about metrics and monitoring and being able to show what the service is doing and being able to make sure that the service is operating properly. And then level 5 is autopilot, which means that it can auto scale, it can scale out, it can scale in. If things crash, it can replace those parts, things like that. So when you start out implementing an operator, first you implement a level 1 operator, and then you try to make it more and more sophisticated, add more and more functionality to it to make it manage the service better. You can ultimately implement an operator with any technology you want, or at least anything that you can deploy and run in Kubernetes. But there are 3 main technologies that are used to implement operators: Helm, Ansible, and Go. So Helm is Helm charts. Ansible is the configuration capability for Kubernetes, and then Go is the Go programming language. The thing to recognize about Helm is that you can only use it to implement level 1 and level 2 operators. So it's the simplest way to implement operators, especially if you're already familiar with Helm. But it can only implement operators that are level 1 and level 2 level of sophistication. If you want to go all the way up to levels 3 through 5, then you need to use something more sophisticated. Usually that's the Go programming language. Something like 70% of the operators in Operator Hub are implemented in Go. So that's usually the way you would do it. Last but not least, here's a few resources you can go to learn more about operators. The first one is a series of articles that my team has written on introducing you to Kubernetes operators. The second one is an ebook that's available from Red Hat. Also, here's where to go find the operator framework, which is a good website for learning about operators and getting the SDK for developing operators, things like that. And last, here again, is the URL for Red Hat Marketplace. Thank you very much for your attention. I hope you found this helpful.